Okay, so today we will see a bit how we can analyze microarray data using some simple linear models. We will see two approaches, one simple one using the LM function in R, and a bit more complicated way using the design matrix and the contrasts. Okay, let's start again with microarray data. So we know that microarray data can be represented by a matrix, in which matrix the columns usually are individuals and the rows are the genes. So for example here I have individuals that belong to two classes. Class 1 is the condition 1, for example healthy individuals, and class 2 is the condition 2, for example individuals with some disease. And for every gene here we measure the expression level of this gene for every individual. So what we have eventually is a set of measurements for healthy people for the gene 1 for each gene, and a set of measurements again for the gene 1 for a second set of individuals characterized by some condition. So here we have some values. I will just write v1, v2, v3 and so on, and here we have some values vx, vx plus 1 and so on. Now usually in microarray analysis, since we have some conditions, not only one, we are interested in detecting which genes show different behavior between these two classes, and by different behavior I mean that we are interested to find genes that, for example, are lowly expressed here compared to this class, or highly expressed here compared to the other class. So if we want to visualize that, here we have condition 1 and here we have condition 2. So we are interested in finding, and here the y-axis is the expression level, so these values here. We are interested in finding genes that are either have this profile, low in this class and high in this class, or vice versa, high in this class and low in this class. Of course, real data will not be, or probably will not be so clear like in this example, but it might be the case that we have some values here in condition 1 with some average value here and some other values like that, which is have this average, and the difference between the averages is so big. And if we have enough measurements here, we can maybe show that this difference is statistically significant. So what we try to find is to detect these genes here where the difference between these two classes, the average difference between these two classes, is statistically significant. Now, okay, I will just write this here. So genes which have statistically different average values or mean values between the two classes. Okay, and in previous classes we have seen, previous courses we have seen how to do that with t-test, and now we will see that with LM, with linear models. Okay, let's go ahead now to linear models. Okay, so a linear model can be written in this form. So here we have the expression value, which is the value that we measure. Let's say that we focus now on gene 1. A similar process we will apply it in every gene here. Okay, if we focus in gene 1, so each of these values is an expression value. And what we try to achieve is to explain these expression values in terms of a factor here. So the factor here might be or should be the condition that we have here. So if here we have healthy people and here we have sick people, so the condition might be health eventually, and this condition has two levels. One is H and the other one is S. So a person considering health might have one of these two states, either being an H or being an S. We believe we are interested in finding genes which are affected by this condition, and therefore in order to find these genes we want to explain these expression levels here by using this condition here. And if we find genes that fit well this model, so fit our explanation of gene expression based on this condition, then these genes are those genes which have been affected by a person being either healthy or being sick. Okay. So what we want to achieve is to explain the expression value using a linear model, a simple linear model of this form here. So we say that the expression level can be written in the form of a constant value, beta 0, plus the effect, if exists, of this factor. And the factor here is the health factor, as I said before, that has two, or it might be a continuous factor as an age, or it might be another factor. In any case, the expression level can be written in this form. And I said that this factor here might be continuous or might be discrete, as I have written here. Now let's get first a continuous case, which might be more familiar to us. And let's suppose that we have that this factor now is the age, is represented by the age. So here we have age, and here we have expression level. So in fact this is like a function. So we assume that the expression level is a function of the age of this factor here. Now let's assume that we have this case here. So each dot here represents the expression value of a person. Okay, let's suppose that's something like that. Now we have all these measurements. Perhaps there are 1, 2, 3, 4, 5, 6, 7, 9, 10. Perhaps there are something like 20 measurements here of different individuals that have different ages. So the age of this individual is this one, age 1. The age of this individual is this one, and the age of this individual is this one, and so on. Now what we observe here in this simple case is that the age actually does not seem to affect the expression level so much, because for all ages that we have measured, the expression level seems to be nearly constant or around this line here. So this is like the average value of these guys, and some values are over that, some other values are below that, but does not seem to have some trend here. Now, another case for another gene might be the following. So again, here we have the age, and here we have the expression level, and if what we see from this data very clearly is that as the age increases, the expression value increases up to some certain age, but later on, as the age increases, the expression value drops. Now, on average, again, the expression value can be described by a line like that. Some values are above this line, some values are below this line. So if we try to fit a line, not a curve, a straight line on this data, so we are not allowed, for example, to fit something like that. These are two lines here. But if we are forced to fit one line, then the best line that will explain the data will be this one. And again here we see that it seems that the expression value does not change with the age, which is obviously wrong because the expression value increases with the age and then decreases again. But if we are forced to fit a single line, straight line, then what we see is something like that. Now, in this case, we say that the data probably cannot be explained linearly because there is no such a single line that can explain the data so well. And if we try to do that, then we will conclude that the expression value is not affected by the age, whereas in fact it is affected. Okay, now let's go to another case, which will be the case that we are mostly interested in this class. And here again we have the age, and here we have the expression, and perhaps the data is like that now. So we have several individuals with these ages here, and what we observe is that there is a tendency for the expression level to increase as a person gets older. And now if we are forced to fit a single line here, it will be probably something like that. A line that passes through the points, and what tells us is exactly that when the age increases, then the expression value increases linearly. Now this word linearly needs some explanation, because what we have managed to fit here in this data is the following model. We have fitted a model which says to us that when we increase the age by a value of 1, so if here we have x, here we have x plus 1 for the age, then the expression level changes so much, so this is the delta of the expression level, and this change is not affected by the age itself. So it doesn't really matter what is x here. We can increase the age from this point to this point, so this will be m and this will be m plus 1, and this plus 1 increase will always change the expression level by the same amount delta x. So what we try to do here is to fit a model that actually explains the expression level with these constraints here. Now obviously this is not correct if the data would change like that. For example, if we increase the age by 1 unit here, then the expression level will change by a tiny amount, so this one here, but here if we increase the age by 1 unit, then the expression level will change by a large amount. So here in this data, the change in the expression level depend on the age, depend on from which age we start. Here the change in the expression data does not depend on the age that we start, so either M or X here. With linear models we try to fit straight lines and lines of this form, and so the genes that are actually affected by the age are genes that have such a behavior here. So this gene, for example, is not affected by the age. This gene is affected, but we cannot find it with linear models. This gene is affected and we have a good fit. This gene is affected by the age. If we fit a model, linear model, probably it will be something like that, and we will find that this gene is affected by the age, but this line is not a very good fit on the data, because actually the data change like that. Okay, we will focus on simpler cases that follow this example just to explain in more detail how we fit the linear model. Okay, now if we have this data, the black point is our expression measurement. This point here on the y-axis, so this expression here, this point here tell us what we predict the expression level to be when the age is 0. You can see that from this formula as well, from this function. If the age is 0, this term will become 0, and therefore the expression level will be equal to beta 0. And again, this might not be an actual expression level, so it might be that no individual actually has this expression level, but we predict that if an individual is of age 0, then, or if individuals are of age 0, then the expression level of these individuals will be around this point. So it might be like that, for example. So this is the average expression level of individuals being of age 0. This is our prediction, in other words. Okay, so this beta 0 is called an intercept, and it's our prediction for the expression level when the age is 0. Now, when the age increases, as we said, by 1 unit, wherever this age is, so it might be here or it might be here, and this again 1 unit, then what this model predicts is that the expression level will change by some amount, which is equal to beta 1. So this quantity here, beta 1, is called slope, and it is the amount of the expression level that is achieved, we take when the age changes by 1 unit. Now if beta 1 is positive, then this function looks like that. If beta 1 is negative, as you can imagine, the data probably will look like that. So what we have here, again, a linear model fits the data well, but in this case, when the age increases by 1 unit, then the expression level is predicted to decrease by this amount here. Since the expression level is predicted to decrease, then beta 1 will be negative. Or in other words, expression level can be written by beta 0 plus beta 1 of h, but since when we increase this, the expression actually decreased, then we are forced to have this coefficient here being negative. Okay. And when we apply the LM function in R, and we have the expression level, and we say, okay, explain please the expression level as a function of the age. So we use this symbol here for this in R. Then R will perform a statistical evaluation of the significance of age on the expression value, and we will see an example now.